Alright, so this is where we left off. Again, organisms in any ecosystem are going to be sensitive to large temperature changes, and we said that reservoirs can absorb or supply finite amounts of energy without undergoing a significant temperature change. If we supply or remove significant amounts of energy and we experience significant temperature changes, then that can devastate the ecosystems. We see this with hydroelectric dams. So when you build a hydroelectric dam, the ecosystem downstream of that dam has a very specific temperature range that those organisms are going to survive. If you pump nothing but the cold water from the bottom of the lake, like say take Hoover Dam in Nevada or somewhere like that, where you have this, you've built up this dam and you've created this very large, deep lake, and the water at the very bottom of that, where there's the highest pressure, is going to be very cold. If you just simply use that highest pressure cold liquid out of the bottom of that lake, and that's all you send downstream, that's going to destroy the ecosystem downstream. Right? Again, you can't, the marine life or any ecosystem is not going to experience a large temperature change very well. Same thing if I put a power plant next to a river or a lake, if it's a coal fire or a nuclear power plant or a natural gas power plant, a lot of times we find in this part of the country, those are going to exhaust large amounts of heat, and that's okay if we spread it out, but if we concentrate too much heat into one lake or one river, that can devastate that ecosystem. So we just have to be aware of that. Again, a reservoir, as I've underlined, can only absorb or supply finite amounts of energy, not infinite. Okay? And because they're real systems, right? They're not ones we go to the physics store and buy that can absorb infinite amounts of heat. Sinks and sources. Right, so a source is any reservoir that supplies heat. A sink is any reservoir that absorbs heat. You've probably heard the term heat sink. That's this big hunk of aluminum that you find a lot of times in electronic devices that are attached to something that generates some electronic chip that generates a lot of heat. You glue a big hunk of aluminum to it. That aluminum will absorb the heat from that electronic device and dissipate it. And that aluminum hunk's going to have big fins that you can blow fan through, a cooling fan within the device, and that's going to very quickly move heat away from the sensitive electronic chip into the big hunk of aluminum, and then air flowing through that hunk of aluminum will move the heat then out of the system. Okay. So, again, source and sink are sources of any reservoir that can supply heat. A sink is any reservoir that will absorb heat. Now, it's real easy to convert any form of energy into heat. Right? Take your hands, you rub them together, and you're generating heat. Anytime your muscles move, they're going to generate some heat, and you can exacerbate that by creating friction there. You're generating heat right now. Your diaphragm muscles are causing air to be drawn into your body and then exhaling that air back out. At least we hope that's the case. Things get difficult if that's not actually happening. So that process generates heat. So anytime, it's very common to take work or any kind of energy and turn it into heat. That's happens spontaneously. It's a lot more difficult to turn heat into work. So we've got an electric resistor here, and we're saying the current is 0. So what I'm saying there, all right, let's say that we go buy an electric heater, a little space heater we might use in the winter. Okay, so we go purchase this heater. Right? Maybe it's got a little fan in it and some coils, and it's got an electrical plug. Okay, and you put electricity in, and it puts heat out. That's real easy. Now, let's say that I don't need this in the summertime, right? So, but you know what I do need? I need a cell phone charger. I'm going to go camping. I need a cell phone charger. So I'm going to go take this thing and, right, campfire. It's going to put heat into this thing. And I'm going to take my cell phone charger and hook some wires up to it and hook it up to the plug of this thing. Hook up my cell phone charger. And I'm going to get electricity out. What do you think? Is this going to work? Take this space heater that normally I put electricity in, it kicks heat out. What if I supply a heat source to it, it puts heat in, can I get electricity back out of that? Is that going to work? They actually, I mean, we laugh. They actually do make devices that will do this. They make devices that you can take hunks of hot burning wood out of the fire and put into it, and it will actually generate a little bit of electric current. But those are very specialized devices. That does not happen spontaneously. This, the electric heater that I would use in the winter would not work in this fashion. That does not work that way. Okay? It is difficult to convert heat into usable work. There's some reasons for that, specifically the second law, but we're going to talk as we go along. Once we get done with chapter 7, we'll talk a lot more in depth as to why that does not make sense. But there are devices that do this. There are devices that we call an engine. An engine is a device that will take heat transfer, it will absorb heat, and it will generate work from a portion of that heat. Now, the second law dictates that not all of that heat can be turned into work unless there's one very specific and impossible to achieve condition occurs, called absolute zero. Another story. Well, it's possible we could reach absolute zero, but it's another story to maintain an engine that operates at absolute zero. Okay, I digress. A heat engine is a device that absorbs heat and converts part of that heat energy to usable work. And that work then can be turned into electricity, it can be turned into motion, it can be turned into a rotating shaft on a motor or an engine that we can use to drive wheels. Whatever we want to do with this work, we can take some heat and turn it into work. That's an engine. Okay? So, they receive heat from some high temperature source, convert part of that, so you see all of this heat coming in, big amount of heat coming in. A little bit of that heat goes out as work out. Whatever you can't kick as work out, you've got to get rid of. Why? Because you don't want it to blow up. Right? If I keep dumping heat into it and only some of that work goes out, some of that heat goes out as work, where does the rest of the heat go? It has to be conserved. Well, if it's not going out here, this thing's just going to overheat and blow up or stop functioning, one of the two. To keep it operating, I've got to reject the remaining heat to some low temperature sink to get it out of the system and continue to operate the device. Okay, that's roughly kind of how an engine works. They operate in a cycle. There's going to be a fluid within the engine we call the working fluid. That's whatever the media is that's used to move energy throughout the engine cycle. Most of the time we will use water because it has such a very high specific heat content. It's not very corrosive, it's not toxic, it's pretty easy to obtain, it's pretty easy to handle, but again the big thing is it's got a very high specific heat content compared to most other substances we would have readily available. So we will often use water. We can use air, nothing wrong with that. We could use R-134, or we could use some other refrigerant, we could use ammonia. Any of those will work just fine. This is a heat engine. I'm going to draw this for you. I want you to draw this in your notes as you're going along. Okay, if you're taking this seriously and you're not just sitting there falling asleep to my videos, you're welcome to do that if that works for you, but I don't know that you're going to get anything out of this. let me draw this with you, okay? So go ahead and let's start drawing this. I'm going to draw a boiler. A boiler is a heat exchanger. So you're going to have some kind of hot stream, probably air or something like that, flowing through this thing, providing a heat input. And then you're going to have this cold stream flowing through it of high pressure, I'm going to say high pressure, low temperature liquid. Alright? And it's going to come out high pressure, high temperature. Right? Liquid, if I'm using air, it's probably not going to liquefy in this thing. But if I'm using water, we're going to probably pump liquid water into the boiler. High pressure liquid water into the boiler, subject it to a large amount of heat at a very high temperature. That's going to generate high pressure, high temperature vapor coming out. So I'm going to have high pressure vapor that I'm going to pump into a turbine. Again, what is a turbine? A turbine is a device that's going to extract energy from a fluid stream in the form of work or power, if you like. So this thing's going to extract work energy out. It's going to come out of the turbine at a low pressure and we'll say low-ish temperature. It might be a saturated mix. We might get it all the way down to saturated vapor and stop. It might get down to a high quality mixture. Who knows? Depends on your turbine and how efficient it's running and how low you want to run it. Then we're going to have another heat exchanger. Again, I've got to get condenser. I've got to reject the remaining heat. So I'm going to have a condenser, another heat exchanger on the bottom. So a hot stream coming through of this vapor coming off the turbine, or a mixture coming off the turbine. I'm going to reject heat and have low pressure, low temperature. If it's water, I'm going to get it all the way down to liquid. So low pressure, low temperature coming out because it's been cooled down. And then I need high pressure to go back into the turbine. There's nothing in the boiler that's going to increase the pressure. So I need to increase the pressure somewhere. And the way I do that is if it's a liquid, that's real easy. I just put a little bit of work into a pump. So a simple way to draw a pump is just a triangle with a circle. This diagram symbol they've got in the book, a lot of times that works just fine too. Interesting thing here. Does any mass cross the boundary? Well, it depends on what is the boundary, right? If I say, well, the boundary is around here. If this is my boundary,